to switch the, now you should be a host. Could you share your screen?
Yes, hang on a sec. This is what I want to do here. Can you see my mouse and my screen?
Yep.
Okay.
Okay, are we ready to go? All right, well, it's great pleasure to welcome Michał Splalinski, who's going to talk about trans-series resurgence and hydrodynamics. Thanks, Michał.
Thank you for the introduction. Hi, so I'm going to review an area of application for asymptotic methods, which has grown out of let me just check, which has grown out, does this work? Sorry, let me just, I think I'm not full screen, and okay. Yeah, I'm going to discuss an area of application of asymptotic methods, which has grown out of phenomenological studies of heavy ion collisions, specifically of the dynamics of quark-gluon plasma created in heavy ion collisions. So the sequence of events, as imagined by an anonymous artist, is given here in these pictures. So one has some nuclei accelerated to relativistic energies which are approaching each other. They collide and form some state of nuclear matter, which then expands, and its energy density drops so that at some point hadrons appear. That's this picture here. And then these hadrons are detected in some kind of apparatus like this. So the point here is that the system is created in a very anisotropic state. So this second picture here shows this post-collision state, which is expanding along the collision axis, which is horizontal, and is initially not expanding a lot in the transverse directions. So the state is very anisotropic, yet after some time, well, by the time that hadrons are formed, one can actually figure out that the system is not far from local equilibrium. So the question is, how this process occurs. Now, the important point is that the measured hadron spectra retain some memory of the initial state. So what we mean by that is that if these nuclei collide slightly off center, then the distribution of these, well, here I guess, of these particles flying out will not be isotropic, and this is what is observed, and that's why we say that quark-gluon plasma is a fluid rather than a gas. So that was actually a sort of open question at the end of the, well, it was posed at the end of the 70s, but it was finally answered, I think, in 2005 with these experiments at RHIC, where it turned out that what happens at least at these energy densities is not the creation of a gas of quarks and gluons, but rather a state which has some collective behavior, and that's why we say it's a fluid. So by the time hadrons form, this fluid is indeed close to local equilibrium, so it is natural to apply fluid dynamics in its description. However, at earlier times, especially close to the collision time, the system is definitely far from equilibrium. And people have been wondering ever since the first successful simulations of hydrodynamics in the early 2000s, why is it that that hydrodynamics is working? And so some questions which arose are, for example, what is the domain of applicability of hydrodynamics? So the textbook answer is that one has to have local thermal equilibrium, but it seems that this is maybe a little too stringent. Then the question I just mentioned are these hydrodynamic simulations which are used to analyze experiment and are found to be good, accurate. I mean, accurate to some degree at least, are they justified? I mean, why is it that one can use hydrodynamics at very early times? Then finally, it has been realized that in fact there are many hydrodynamic models which one can use to evolve some initial data, and it's interesting to ask, is there some way to formulate hydrodynamic models systematically and compare them, match them to some microscopic theories and so on. So this sort of textbook field of hydrodynamics has suddenly turned into a very dynamic and very vibrant area of research. So a lot of this research was carried out in the context of idealized models where one could observe, well, observe mathematically at least, how a far from equilibrium system tends toward equilibrium. And the work that I'll be discussing can be divided up into three parts. One is hydrodynamic models, that is well, I will explain in a minute what I mean by that exactly. Then models of kinetic theory, and finally a specific model, which is the n=4 supersymmetric Yang-Mills theory, which can be studied using the ADS-CFT correspondence in the strongly coupled limit. And in this limit, hydrodynamics emerges very naturally. So in fact, this third point here was very influential and shaped, I think, the development also in these other categories. So in this talk today, I will not really say anything about kinetic theory because well, there's just enough other things to say. So I will begin with discussing hydrodynamic models. And the reason why this is a talk at this conference is that there is a sort of universal language that has been adopted by people thinking about these things. And this is a sort of perturbative approach, which is called the hydrodynamic gradient expansion. And this is a gradient expansion in the sense of space-time gradients of some natural variables. And the nice thing in these idealized models that I'll be talking about is that it is possible to calculate explicitly many terms in such expansions. So it's a pleasant area to be studying asymptotic methods and large order behavior, because it is not outrageously difficult or expensive to calculate a lot of terms. Okay, so I'm going to begin by saying what I mean by relativistic hydrodynamics rather than a hydrodynamic model. So this is an attempt to use words somewhat more precisely than everyday usage. So the basic point of departure is the statement of energy momentum conservation, which is written here. So we of course have to use relativistic hydrodynamics because we're mostly interested. I mean, the motivation for my research has been the dynamics of quark-gluon plasma. So the conservation equation is the covariant conservation equation of the energy momentum tensor, and this is a statement. So I'm imagining here that I have some microscopic theory. Of course, ideally this would be quantum chromodynamics, but in practice, one is willing to accept simpler models oftentimes. But this is an exact statement. And in particular, one can, if this is taken to be, let's say, an operator in quantum field theory, or I'm not really being specific, but from this, by some sort of averaging or taking expectation value in the state of interest, one ends up with a classical object. So this team you knew now, I'm going to think of as a classical field, let's say, and one can express this energy momentum tensor in this perfect fluid form, plus some corrections. So the variables which appear here are the energy density and the pressure, which are thought to be connected by an equation of state. And then if we have an energy momentum tensor calculated as a 4x4 matrix, so I'm going to stick to 3 + 1 dimensions. So we can imagine this is a 4x4 matrix, and this eigenvalue problem may have solutions with time-like 4 vectors u. So that's what's appearing here. And if the state that we're calculating this expectation value in, if that state were an equilibrium state, then we would just have these terms, as is well known, that just this perfect fluid form. But if this is not an equilibrium state, if it has some gradients of these hydrodynamic variables, the flow velocity and the energy density, let's say, then there will be gradient. Well, there will be some corrections here, and what is meant by the hydrodynamic gradient expansion is having or anticipating having an infinite number of terms here, which are graded by the number of derivatives of these hydrodynamic variables. That is the energy density and the flow velocity. So pi n is a contribution which has exactly n gradients, and importantly, we are inserting a sort of gradient counting parameter epsilon, which is a formal parameter, which will at the end of the calculation set equal to 1, but it is there to organize this perturbation expansion. And the basic point which has emerged over the past 10 years, let's say, is that these gradient expansions in all the models that have been analyzed, essentially all, barring some pathological, let's say, very fine-tuned situations, are divergent. So I mean, they have 0 radius of convergence. And in my talk today, I will go over some of these situations where this expansion becomes divergent. By situations, I mean models. Models of basically 2 types. So mostly I'll be talking about the hydrodynamic models, which I will turn to now, and then I'll mention also what the picture is in Yang-Mills theory. Okay, so now what I mean by hydrodynamic models. Okay, so this is a change of perspective. So of course, for perfect fluids, we are all used to the theory of perfect fluids, which is formulated in terms of the energy momentum tensor expressed in terms of classical variables u and epsilon. Again, p is a function of epsilon. And if we have a system which is very close to equilibrium, then then this is enough. We do, we may not be able to observe any gradient terms, and this describes any such near equilibrium system, including, of course, equilibrium. And the microscopic information about what it is that we're looking at is contained in the equation of state. Now, in this talk, I will adhere to the assumption that has been made almost in all the models that, certainly all the models that I'll be talking about today, and that is that the system is conformal. There is no scale. It's invariant under scale transformations. And in such cases, the equation of state is just telling us that the pressure is a third of the energy density, and the energy density itself can be written as the 4th power of some effective temperature with a coefficient which is dimensionless. And this quantity T, if we're talking about a near equilibrium state or equilibrium state really, then that would be actually the absolute temperature. Otherwise, it's just a formal variable, which is the 4th root of the energy density. So the statement, the equation of energy momentum conservation, this is no longer viewed as a statement. It's an equation of motion now, And the whole thing works because there are 4 equations and 4 variables, so the energy density and 3 components of velocity. So that's the perfect fluid theory that we all know and love. Now, in heavy ions, perfect fluids are not really enough because quark-gluon plasma in those circumstances behaves as a dissipative system. And so one has to add something that vanishes in equilibrium because, well, this here, I used the equation of state, so now I've eliminated the pressure in favor of the energy density. So this vanishes in equilibrium, and but away from equilibrium, it's not it doesn't vanish, it's not zero. And if you want to have classical equations that you could solve, you would need to express it in terms of these variables. And the simplest possibility, which is to set this equal to just the first derivative of the flow velocity with some coefficient. And so, of course, this object has to be a Lorentz tensor, which is symmetric in both indices. And in fact, in a conformal theory, it also has to be traceless. And there are some conditions. So that's why I wrote this calligraphic derivative here, because it hides some terms that have to be added, that have to be present for consistency. And there's some scalar coefficient, which is a function of the temperature or this energy density. This is the shear viscosity. So this would be saying that this dissipative tensor is given by the most general thing you can have in a conformal theory at order 1 in the gradient expansion. So I've skipped the epsilon here. The epsilon is 1. So this is simple, but the problem is that in a relativistic theory we want to have causal signal propagation, and this theory, that is the covariant conservation of this object, viewed as equations of motion for u and epsilon, these equations are unstable and acausal. Well, by unstable, I mean that the state of global equilibrium is actually explosive. So one has to fix this somehow, and one could think that adding more terms here will help, but this does not help in the sense that the theory remains acausal and unstable. So one possibility that has been explored a lot in the last 15 years is an approach where this dissipative tensor is viewed as a set of additional variables, and one has to provide an equation of motion for this object, so not just eliminate it in favor of derivatives of the hydrodynamic variables, but actually provide a bona fide equation of motion. So this we might call a dynamical constitutive relation. A relation which expresses the dissipative tensor, well, doesn't express it, but relates it to the hydrodynamic variables, but not in this sort of explicit way, but rather through some evolution equations. Okay, so the most simple thing that one can have is this Israel-Stewart theory, where one posits a relaxation equation for the dissipative tensor. So again, there's this derivative which hides some details, but basically this is a relaxation equation which describes how this pi exponentially goes to this source, right? So the idea here is that if we could ignore the relaxation time, so here there's a new scalar parameter which could be a function. Which is in fact a function of the effective temperature. But if we could ignore this, then that would be the equation from the previous slide. But adding this turns out to have very important effects, including restoring or regulating the causality problem. One can look at this also in the following way, that this is some linear, I don't know if linear, but anyways, it's an operator acting on, well, it's linear in so far as it acts on pi. And so we can just formally solve this equation. So we can say that pi is the inverse of this operator here, the inverse acting on the right-hand side, on the source. And then one can just expand this in some kind of geometric series. So this is a sort of formal manipulation, but the point is that one sees that an equation like this can be viewed as generating an infinite series. So this infinite series, which is nothing but the gradient expansion, except that before we had it truncated at order 1. So this was the Navier-Stokes theory. But this Israel-Stewart theory, in fact, has all these terms of all orders. Before I go on, I want to say that the shear viscosity, this parameter eta, and the relaxation time, which we introduced here, they have to scale in the right way with the temperature, because this is a scalar invariant theory. So in fact, the relaxation time has to be equal to some dimensionless number, which I called C tau, divided by the effective temperature. This gives it the right dimensions. And the shear viscosity has the dimensions of entropy density, which is temperature cubed. And so it has to be proportional to it, because there's no other dimensional entity, with some coefficient C eta. So in some theories, this C eta has a value of 1/4 pi. This is this KSS Kofton-Starinets Kofton-Son-Starinets calculation, this famous eta over S equal 1/4 pi. But we will just keep C eta here as a free parameter, and C tau. So the subsequent equations are going to have these parameters in them. So the first thing one can do in this type of situation is to look at linearized perturbations of equilibrium. And if one takes those equations, and delta phi is now basically it's like a common vector of the perturbation of the energy and velocity and so on. So if one linearizes them, one gets some sort of linear equation, and it's going to have solutions in this exponential form, where omega is a function of k. And I've written it here as a series in k, because for various reasons. Well, sometimes we can't get a closed formula for omega of k. We can just get some equation which determines it, and then we can solve it like this. Sometimes we can have a closed form solution. So in this particular theory that I was talking about on the previous slide, this Israel-Stewart theory, the solution as a series involves well, there are solutions describing sound modes, which are basically longitudinal modes in some sense. And the frequencies then are given here. So there is, are given here and here. Okay, so there are two modes, two hydrodynamic modes, which describe propagation of sound along the z-axis, one or the other. And there's also importantly this frequency here, which has a constant negative imaginary part, which remains there when k goes to 0. So the importance of this is that this describes a non-hydrodynamic mode, which is exponentially damped even at long wavelengths. In other words, even when k goes to 0, this is damped. So we imagine these modes as being long-lived, provided they have long wavelengths, whereas these modes are short-lived because they are damped by this quantity. And in fact, it is the presence of these modes which makes this theory causal, well, at least at the linear level, makes it causal at least at the linear level and stable. So one gets some conditions for stability of equilibrium. And also, if we compute the group velocity of these sound waves, we find that the velocity remains below the velocity of light, which has been set equal to 1. I don't have C here, it's 1. When the relaxation time is sufficiently large compared to the shear viscosity. So this non-hydrodynamic mode plays a crucial role in this hydrodynamic model. It acts as a regulator which makes causality possible. And these non-hydrodynamic modes and their role is the key point, I think, of the last 10 years in this area. And they manifest themselves in in these divergent series, as I will discuss in a moment. So now I want to have a closer look at this equation, at this series, because it turns out that this series has a finite radius of convergence, but that radius of convergence, in some sense, determines the convergence properties of the gradient expansion, right? So this is not the gradient expansion. This is just the presentation, let's say, of the dispersion relation, but as a series. But in fact, it affects the gradient expansion in the linearized theory. Okay, so the point here is that in some cases you can actually explicitly see what this omega of k is. So, for example, for shear perturbations in this theory that we're discussing, you can get an explicit formula which has a square root, and so there's some value k star where we have a branch point, and the existence of this branch point is the position of the branch point sets the radius of convergence of this quantity as a function of k, it was found a couple of years ago that in fact this omega of k as a series can be related to the gradient expansion at the linearized level, and I'm going to skip a lot of details, but the basic point is that the theory contains this k star, which is a branch point in some dispersion relation, which is an intrinsic property of the theory. In other words, we can calculate it once and for all. And now the gradient, we can look at the gradient expansion of the constitutive relation. The gradient expansion, I've been saying the gradient expansion, we can look at it and ask, is this convergent for given initial data? So what turns out to be the case is that the key feature of the initial data is its support in momentum space. So if the initial data has support bounded by some value k max, then the gradient expansion will be either convergent or divergent, depending on how k max is related to k star. I mean, what the ratio is, let's say. So this is shown in this nice nice picture. So k star is this dashed value, and if the support of the initial data is below k max, then the gradient series will actually be convergent. However, if it exceeds k max, it will be divergent geometrically, and in the generic case, when k max is where there is no momentum cutoff, because the existence of a finite maximum value for the support in momentum space is some kind of a cutoff, right? So if you don't have a cutoff in your system, then the gradient expansion of the linearized theory is factorially divergent. So that is I would say the generic case. That, however, if you introduce a cutoff by some means, and I will in some example later, we will see that the factorial divergence becomes geometric. And this argument I've presented in a very sketchy way, but it holds generally whenever the dispersion relation has a branch point. So this is I would say a fact. And now whether the dispersion relations have a branch point is not, I would say, a watertight conclusion. However, it is believed to hold in any causal theory. In other words, you can write down examples where there is no branch point. For example, the Navier-Stokes theory, it has no branch. There's no branch point there. Then the theory will not be causal. So that's the situation at the linearized level. Now, at the nonlinear level, we can't really do numerical or analytic calculations completely generally. So what has been done in the past 10 years or so are studies in various idealized systems possessing some additional symmetry restrictions. So there are three prominent examples. Well, prominent, I don't know, but the most prominent, I mean, certainly the first example is prominent. I mean, this has been studied for a very long time, Bjork and Flow. So this I will discuss in a second. There are many, many very explicit calculations that have been done there. More recently, there's a class of flows called longitudinal flows, which are in some sense nonlinear sound waves. And I will discuss this in a moment. And there's also other restricted kinds of flows, for example, Gubser flow. But I will only talk about these two today. All right, so Bjork and Flow is I hope not to spend too much time on it because I know there'll be other talks later where this will be mentioned, I imagine. But very briefly, so this is another picture of how the nuclei collide. They collide along the z-axis, and this picture shows the time evolution of the plasma, and so this is something is happening here in the future light cone, and the z and t coordinates are somehow traded here for the proper time and space-time rapidity coordinates. So these sort of radial lines are lines of constant space-time rapidity, whereas these hyperbolae are lines of constant proper time. And the color coding suggests, and there are physical reasons for this that I won't discuss now, but there are reasons to believe that at least at the initial stages in some kinematic region, it is true that the physics depends only on the proper time. So basically the colors follow along the hyperbola, there is no color change, right? So the physics depends only on proper time. So this is the specific relation between the time and z coordinates and the proper time tau and the space-time rapidity y. And then so one thing that I forgot to say is that because this is an ultra relativistic collision, these nuclei are seen as length contracted, Lorentz contracted along the z-axis. So they are in some sense very extended in the directions transverse to the z-axis. So the symmetry that Bjorken introduced in the early 80s, it assumes that there is no dependence on the transverse coordinates and no dependence on y. So the system is boost invariant for boosts along the z-axis, and it's independent of transverse coordinates. So only one coordinate remains. So under those circumstances, the energy momentum tensor can be written in a diagonal form where the 0,0 component is the energy density, and then there's a longitudinal pressure eigenvalue, and there are two equal transverse pressure eigenvalues. And because we're looking at conformal theories where the energy momentum tensor is traceless, then also these two pressures have to be expressed in terms of epsilon and some other quantity A. Okay, this other quantity A measures the deviation from isotropy. If A is 0, then we are in equilibrium. Well, we might be in equilibrium. So the system is then isotropic if A is 0. So we have two functions, and these are functions only of proper time. So now the equations of hydrodynamics, in particular, this Israel-Stewart theory or other theories of that kind, they now take the form of ordinary differential equations, and there are two of them. There's the conservation equation and this Israel-Stewart relaxation equation for two functions, which is A and this epsilon, and we're going to be trading the energy density for this effective temperature for most of the time. So you can see that, I mean, it's clear that you can just write those two equations as a single equation if you like, and then one gets this equation. So these two terms at the end, they correspond to the perfect fluid approximation, and so this is then the Navier-Stokes, the viscosity term, and this corresponds to this relaxation time terms. And you can see right away without doing any calculation that at large time, large tau, large proper time, these terms will be subdominant, and one just has these terms, and that gives this famous Bjorken solution 1 over tau to the 1/3. And if one wants to take into account these other terms, there's a whole series that's generated. So there are the three dots indicate the remaining terms in this perturbative series in inverse powers of tau to the 2/3. But there is also clearly something else here, this ellipsis here. And the reason why we know there has to be something else there is that this equation is a second order equation, so it has 2 integration constants, whereas this asymptotic solution contains only one integration constant. So half of the information in the initial state is lost. So this is good. It's a dissipative system. That's fine. But from a formal point of view, we would like to track what happens to the rest of the information. And that rest of that remaining information is, of course, hidden in exponentially suppressed terms, which cannot be represented as this kind of series. Now, we could develop this whole thing starting from this equation, and of course that was done. But there's actually a sort of more convenient, in some sense, way of looking at things. So we can basically go to a different set of variables which are both dimensionless. That's the pressure isotropy, which is dimensionless by design. But we can also, instead of using proper time, we can use this variable W, which is tau times t, and in the units that we're using, that is dimensionless. So now the conservation equation and the Israel-Stewart relaxation equation can be written in a way which decouples them, right? So the conservation equation involves everything, but here you would think of t as a function of w, and a would have to be given as a function of w, and indeed there is an equation for a as a function of w, which does not involve anything else. So this way of presenting things is nice, because this perturbative solution that we saw on the previous slide is now repackaged so that this equation is going to have a completely universal late time solution. I will say late time meaning late W, large W, also not just large tau. Whereas the scale lambda is going to come back if we plug in our solution for A into this conservation equation. So let me just quickly check how much time I have. I don't know when I started, but I think I started 1/4 or something. I don't know how much time I have, but I'll try to go quickly over this, because this is well, it's already a few years old. The point is that this equation can be solved numerically very easily, and it has at late times completely universal behavior independent of initial conditions, whereas at early times you have all kinds of solutions. But there's also a distinguished solution which is called which sort of extends the hydrodynamic prediction, which is this 1 over W term, to smaller values of W to smaller times. And this solution at early times, it describes a system which is anisotropic, because it's already, I mean, this pressure isotropy is already greater than 1 around here, right? So this is not really what we would call hydrodynamics, but it has been called the hydrodynamic attractor, which extends formally all the way down to W around 0. So from the point of view of heavy ion physics, this plays an important role, but I will maybe not talk about this too much right now, because time is short at this point. The important point is that this attractor is a regular solution, and it's actually one of 2 regular solutions, the other one being repulsive. And whereas these solutions, they behave in this sort of way, independent of the transport coefficients. So somehow this effect is associated with the fact that this is a longitudinally expanding system, which expands very strongly at early times, whereas here at late times, one has some sort of decay of non-hydrodynamic modes, like the ones I mentioned when I talked about linearization. So the whole thing, the whole solution can be thought of as consisting of some perturbative series plus corrections. And this perturbative series, in fact, contains no dependence on initial data, whereas the trans series brings in the dependence on initial data, but it's damped by this exponential factor. So this kind of picture persists in a number of other models of this kind or of other kinds. And roughly the pressure anisotropy can be written as a trans series where W is the evolution parameter. This damping rate is related to the non-hydrodynamic mode, and the factor of 3/2 is understood also. I mean, it's understood where it comes from, so it's not a discrepancy. It's the way it has to be, and so the non-hydrodynamic modes, in other words, in these models, they first of all ensure causality and stability at the linearized level, and secondly, they are responsible for this sort of decay toward the hydrodynamic attractor. So there are some things I wanted to stress. One is that the perturbative series is universal. It has no memory of initial conditions in this very simple setting. The trans series parameter is what carries the initial data. The trans series itself is a sort of metaphor for dissipation of information encoded in the initial state. These series, they come from an ordinary differential equation, so somehow they're guaranteed to satisfy resurgence relations, and one can use Borel summation to extend this hydrodynamic attractor from the hydrodynamic region of large W to earlier times. Okay, so that's I think as much as I wanted to say about Bjork and Flow, about Bjork and Flow in hydrodynamic models. Now I wanted to also mention that these kinds of calculations have been done also in other models, including models of kinetic theory, which in some ways is similar to hydrodynamic models, but actually has some puzzling features, which are interesting, but I won't mention them. But today, before I move on, before I leave Bjork and Flow, I wanted to mention that in fact there is another example where this kind of series appears, and this is this n equals to 4 supersymmetric Yang-Mills theory. So in this case, one in fact has a completely dual, meaning equivalent formulation of this field theory. So the super Yang-Mills theory in n equals to 4 super Yang-Mills theory in Minkowski space in 4 dimensions. It's an ordinary field theory like QCD, but it has some exotic, well, not exotic, but some specific matter system of fermions and scalars. But it's a theory in flat space, in flat 4-dimensional space. But it can be reformulated in a way which looks like a gravitational theory in 5 dimensions. So this is this ADS-CFT correspondence, and the thermal state of super Yang-Mills theory, the equilibrium thermal state, is mapped under this correspondence to a kind of black hole solution. It's called a black brane because the horizon of the black hole in that instance is planar rather than spherical. So the thermal state is this kind of black object in this asymptotically ADS space. By asymptotic, well, it's a space where with asymptotics different from Minkowski space because of non-zero cosmological constant. And the linearized perturbations of equilibrium, these what I called hydrodynamic and non-hydrodynamic modes, now they are mapped into black brane quasi-normal modes, where the word quasi-normal mode is used in the sense that people use it in general relativity. So one has a black object, like a black hole. It's perturbed in some way, and it begins to oscillate in a damped way. And these damped oscillations, these quasi-normal modes, They have well, in this case that I'm talking about, they come in pairs of complex conjugate with complex conjugate frequencies, denoted by A1, A2, and also the conjugates. And so I've written the trans-series solution for the energy density here, not for the pressurized entropy, but that actually can also be computed from this. Well, here it's written, so the energy density here is written as a function of tau to the 2/3, this parameter u. And well, this sum is actually kind of convoluted because there are all these sectors. So one can think of this vector n as that's summed over here as being the components. So these ni are integers, and then these ei are some vectors such that this is true. And the contribution with n equal to 0, that is the hydrodynamic gradient expansion, and it has the same form as we saw in the Israel-Stewart theory. But in that case, we had coefficients here, coefficients of the series, which depend on parameters of this hydrodynamic model. Now, in n equals to 4 supersymmetric Yang-Mills theory, these parameters have values that can be calculated. So C eta is 1/4 pi. C tau has some, there's also some answer. It's like logarithm 2 divided by, sorry, log 2 minus 2 divided by something. It's a specific value. So this series here, the hydrodynamic series, the one which has 0 here, it has completely fixed coefficients by this model. So that's the gradient expansion of the energy density, plus, well, all these other sectors which correspond to the black brane quasi-normal modes. So I mean, it was published already a few years ago, so maybe it's known, maybe not, but anyway, I just wanted to say that it's not just hydrodynamic models where one can study these things. One more important point is that in the case of hydrodynamic models, especially Bjork and Flow, everything reduces to differential, well, in the case of Bjork and Flow, to ordinary differential equations, whereas here this calculation is actually quite convoluted because it involves, first of all, solving a 5-dimensional set of Einstein equations, and then one has to use a limiting procedure to extract from the asymptotic behavior of the metric in 5 dimensions well, basically the energy density, right? So this is not, so this energy density does not, as far as I know, does not satisfy any differential equation as a function of u or tau, right? So this is a function. Okay, I have stressed here that it depends on these trans-series parameters, but in some sense, maybe that wasn't a good idea. The point is, this is a function of a single variable tau, right? But there is no known differential equation satisfied by this quantity. I mean, I can't say there is none, but I just don't know of it. And the way it's calculated is by solving partial differential equations and then going to some asymptotic limit basically to the boundary of this asymptotic ADS space. Okay, so that's as much as I wanted to say about Bjork and Flow. There's a lot more that could be said. In particular, I've skipped kinetic theory completely, but there's a lot of work done there, and it's roughly in the same flavor as I've described here. Now, more recently, there's some progress that I think is quite exciting, and this is these are studies of nonlinear flows in hydrodynamics, in kinetic theory, and also in n equals to 4 super Yang-Mills theory, where this holographic relation can be used also to study such flows. So these are flows depending on T and Z. So basically, so not just the proper time, but T and Z separately. One could say that this is basically incorporating the possibility that boost invariance is no longer a symmetry. I mean, anyway, it depends on two variables. And I will say a few words about how this works in MIS theory, which is the simplest possible situation. So so basically we neglect the transverse dimensions. So in that sense, it's like Bjork and flow, there are no transverse dimensions, but we do not insist on boost variance. So now the for velocity is not fixed. Maybe I didn't emphasize it, but in the case of Bjork and flow, the for velocity u mu is actually fixed to be 1, 0, 0, 0. It's completely fixed, and the only degree of freedom is the energy density and whatever is in the dissipative tensor. Now here, the for velocity is non-trivial. There's some degree of freedom alpha, which depends on T and Z. Well, here it is, here's U. And the dissipative tensor, it can also be written in terms of 1 degree of freedom. So the tensorial, so this has to be traceless and symmetric and so on. But the most general thing you can have under these assumptions is this tensor here. This PT mu nu is a projector onto the transverse directions, so X and Y, let's say, transverse to Z in space. So in the end, we have two dynamical variables, alpha of TZ, pi star of TZ from here, and of course the effective temperature as well, or the energy density. So in the end, there are 3 variables. And this theory at the linear level, it describes sound modes, so modes along the direction of propagation, but no shear modes, no transverse modes. That's what that theory has. And we can study the gradient expansion by writing down this formal series for this degree of freedom pi star. Actually, I guess that should be, oh no, okay, X is like the space-time X, it's Z and T. I hope that's not confusing. Anyway, it's an infinite sum. There's this formal parameter epsilon. I've put it back in, and pi star n depends on exactly n derivatives. So it contains terms with exactly n derivatives of T and alpha. And now the trick is that we take the relaxation equation, the MIS equation, which is this dynamical constitutive relation, and we stick epsilon in there as well. In other words, we put an epsilon wherever we see a gradient. So there's a gradient here, and also here we have gradients. So there's this epsilon here, there's no epsilon there. And then we take the gradient expansion, plug it in here, and you get recursion relations. So the leading order term, you can see right away, it's like the pi 1, it has to be equal to what's sitting here. And then there's more, but they're all determined. And once you know these pi n's, you can ask the question, is this series converging, diverging, or what is it doing as a function of space-time? So to do that, I mean, there are various approaches to this, but the approach that we took is we solve the full equations numerically. In other words, we find we call it the background. I mean, basically, we solve the problem numerically, and then we plug that in to these equations, and we look at the magnitude of the different terms in the gradient expansion. So what happens is illustrated, for example, on this plot. There is some so this direction x, that should be z, I'm sorry, and it's compact. I mean, it's periodic. There is some asymmetric initial condition that's taken, so this is not completely symmetric, but you see the periodicity, so the color basically the temperature, and there are 3 points that are looked at here. These 3 points, and here we plot the root test, I guess, the 1 over n, the power 1 over n of the nth order of the gradient expansion as a function of n. So this, so for factorial growth, these should be straight lines, and they are. So the different points at different points, the different things happen, but it's in each case it's divergent factorially. However, one can this calculation, I mean, the solution of the full hydrodynamic equations is done on some grid, on some lattice, let's say. And if one takes the lattice to be, I mean, if one takes a coarse lattice, I mean, not a very fine lattice, then at some order, you're going to be sensitive to the cutoff, to the momentum cutoff, which is provided by the lattice. And so, in fact, these straight lines will eventually flatten out. And this is exactly the effect that I discussed in the case of linearized flow, when there is a momentum cutoff, a finite momentum cutoff, which is above the some intrinsic scale. Now, this is not a linearized calculation, so we can't really, but anyway, but one can understand where, like from the numerics, one can understand when this effect should happen, and it does happen. But the most important point for me is that at every point here, the gradient expansion, in the sense I explained, is factorially divergent. I'm assuming I still have about 5 to 10 minutes. So we can now study the large order behavior of the gradient expansion in the sense I explained, generated in the sense I explained. So if we just had a series, it is well known for many years that the factorial divergence actually occurs with a power. So basically, the large order behavior of coefficients in such series is that of a factorial or gamma function, possibly shifted by something which actually isn't going to play a role here, divided by something to the power n, possibly with some amplitude. And now the way we're generating these series, these numbers, so this a and this chi, they are, and this alpha, they are functions of space-time, because our series are generated as series in this formal power counting, well, gradient counting parameter epsilon. And this quantity chi is actually very important, because as is known from simple ODE examples, in fact, from the Bjork and flow examples, this quantity chi is what controls the exponentially damped effects. So so there are 2 papers which I want to mention here. This paper where this work that I'm describing is written down, and there's also an earlier paper by these gentlemen who from 2005, where I don't know if this is something that's been done also before or after, but this is the paper which we've identified as somehow a precursor of this procedure. So they also have a partial differential equation. They have some formal parameter, and they also consider these parameters as space-time dependent. So we followed Dingle in calling chi the singulant, and the singulant somehow grows out to be a very important quantity. And this ansatz, you can check whether this ansatz is consistent with the equations of motion. And the answer is affirmative, provided the singulant satisfies its own evolution equation. So this is something that appears in this paper by Chapman and Mortimer. And in Israel Stewart theory, this singulant equation of motion is given by this. So basically a derivative along of the singulant along the flow has to be, I mean, has to be equal to 1 over the relaxation time. And so this is C pi divided by T, in fact. But a better way to think of it is that it's the imaginary part of the non-hydrodynamic mode at 0 momentum with the temperature set to whatever to the background temperature. So here we see that the singulant motion is in fact determined by the non-hydrodynamic mode at 0 momentum. But we looked at other models of longitudinal flows, where in fact it can happen that it is not controlled by the non-hydrodynamic mode. So the significance of this is that that when we talk of non-hydrodynamic modes, we usually mean linearizing the equations of motion. Now here, we are not linearizing the equations of motion. I mean, there is a linearization of sorts going on when we look at the leading large order behavior, but it's not a linearization of the. I mean, we're not like linearizing first and then solving linear equations. The important thing about singulants is that, as I mentioned before, they will control the transients. So we expect that the gradient expansion in these longitudinal flows is going to benefit from exponential sort of trans-series kind corrections, exponentially damped corrections, where the singulant is going to be providing the damping, and one can look at solutions of these singulant equations of motion, and one finds that they travel. So in some cases, they may do something complicated for a while, but eventually they will just grow. The real part will just grow. So in MIS theory, again, there's a very simple picture. So as I said, the longitudinal flow in MIS theory is just kind of nonlinear sound waves. So there are 2 hydrodynamic sound modes and 1 non-hydrodynamic mode. So there are 2 conjugate singulants, and there's this non-hydrodynamic singulant, and the real part grows at late times. So this kind of fits in with this equilibration picture, and you can easily look at, compare the solutions of the singulant equation of motion with the gradient expansion, and it works. I mean, it kind of has to work, but it's satisfying to check that it does. So the rough conclusion I will be finishing up now is that these singulants, they are somehow a generalization of non-hydrodynamic modes to the nonlinear regime. So I have no idea when I should stop, but I'm guessing it should be around now. So I'm just going to say, just to summarize quickly. So this gradient expansion is a perturbative approach to equilibration, where you expand in gradients of hydrodynamic variables, and it has the flavor of effective field theory, because in some sense the general form of the gradient expansion just parametrizes the most general behavior you can expect close to equilibrium. So it's a parametrization of the most general possible asymptotics, let's say. Generically, this gradient expansion is factorially divergent, so a very precise answer can be given at the level of linear response. Loads of examples exist for Bjorken flow. And now there's also this class of longitudinal flows where one can really study this very explicitly, although one needs numerical calculations to do this. The pattern of divergence is captured by singulants, which resemble non-hydrodynamic modes. So they describe the transient, short-lived effects in these equilibrating systems. And there are lots and lots of open questions. I mean, there may not be actually open, but we don't, I mean, the authors, my colleagues who wrote this paper and we don't know the answers. So how many singulants are there? I mean, close to, so one can do this calculation in the linearized approximation, and then one can map singulants to non-hydrodynamic modes, but in general, it's not clear how many there are. How can we find initial data for the singulant equation of motion? It would be nice to be able to infer it from the initial data for the flow, but again, it's not clear how to do that. And of course, there is the more difficult question, perhaps. Well, I don't know if more difficult, but like, can one do this kind of analysis going beyond the longitudinal flows? So longitudinal flows themselves, you know, broke the sort of ghetto of Bjorken flow, but they themselves are also limited. So can one formulate this sort of approach for completely general flows? So some ideas are floating around, but we will see. Okay, thank you very much. Again, I don't know if I went over time or not, but thank you for your attention.
Thanks, Michał. Thanks, Michał. Okay, we're in the late time regime, so maybe one quick question.
Hi, Michał, it's Ines.
Hi, Ines. Hello.
Just to ask a very quick question, the singular approach in n equals 4 separating mills in the on the Einstein equations, how horrible would it be?
Well, it's definitely more horrible than in hydrodynamics, but actually in this paper, this is to some extent, I mean, this is definitely discussed and some calculations are there. It's not impossible. It's not impossible. So yeah, and also in this paper there is a generalization of the model that actually you and I studied back in the day, where one adds terms which somehow make, you know, add terms whose consequence it is. I mean, those terms are somehow engineered to mimic the situation in ADS-CFT, and they break this sort of relation with non-hydrodynamic modes. So yeah, the answer is that it's not impossible, and to some extent, I mean, some beginning has been made, and yeah.
All right, well, we need to move on. Thank you very much, Michał.
Thank you.
See you.